email mistake this morning because I set it up automatically. I forgot to cancel. So we're happy to have Sebastian again, and he will talk about 150-page long new paper that was recently accepted to start this year. Checking covering, please.
Thank you. So this is joint work with Max Gorsky, Ken-ichi Kawarabayashi, and Stephan Kreutzer. And I've highlighted Max's name here because this is essentially his PhD thesis that I'm going to present today. He will be visiting us in May, and because the paper is so long, there is so much to talk about, so I'm pretty sure there will be a second talk on the topic. But because we have the gap, I'm trying to fill in. There is a big disclaimer here. So because the proof is very long and very complicated, what I'm going to do today is an extreme oversimplification of everything. So I will not tell a single thing that's true, but most of it is close to true. Okay. Oh. Doesn't work? Do I have to
press the button?
No. This also doesn't work? Ah, you can click. No, maybe I can just come over here every once in a while. Ah, now it works. Nice. Good. Okay, so the entire project was about packing and covering of even direct cycles. So the first page, this is kind of unusual for me. I will start the first page with the statement of our theorem and some definitions. So I take F here to be a collection of cycles or directed cycles such that no vertex appears in more than Q of these cycles. And in such a setting, I will call F a 1 over Q packing. So this just explains what we had. So we had the quarter integral. So quarter integral means 1 over 4. Most of the time we will see 1 over 2. And sometimes we will see just one packings. I say one packing if the members of F are pairwise disjoint. So now I say a class C of cycles or directed cycles has the 1 over Q Erdős-Pózsa property if there is some function such that for every graph or digraph and every integer k, one of two things happens. Either I find such a 1 over Q packing of members of C inside of my graph G, or I can delete a set of at most f of k vertices from G such that all of the cycles from C vanish. So this is the Erdős-Pózsa property, and in this language our theorem says that the family of even directed cycles has the 1 over 4 Erdős-Pózsa property. This is kind of strange because this is the 1 over 4. Usually you see 1 over 2. This is mostly because the analysis we have at the moment only gives 1 over 4. This is what I alluded to earlier. So with high probability, Max will try to explain how we get from 1 over 4 to 1 over 2 in May. But for the moment we stay at 1 over 4.
So if there's a possibility that the 1 over 2 may still work?
I think it's true, yeah. So the 1 over 4 seems to be artificial from the way we go through the proof. So what I have here, this will be a reoccurring picture. This is the cylindrical wall or cylindrical grid. This is somehow the directed analog of the grid theorem of Robertson-Seymour, and that's the object that comes out. And I'm going to modify this a little bit. But before I do, one nice thing to observe here is that all of the directed cycles in this object kind of separate this internal disk from the disk outside. So there's these two major faces, and every single directed cycle moves between those two, and there's no other directed cycle. So I can go further in and come out again sometimes, but I can never go backwards. This is a very important property. At the moment, all directed cycles in this guy are of even length. But what I can do is I can do two modifications to this. First, I can subdivide each edge here. So this makes it such that every cycle that goes around is now of odd length. And then I have these little jumps on the outer face. all of them allow me to shortcut this, or not shortcut, to extend, instead of taking this edge, take this and add one additional edge to the cycle. So now if I go around and pick up one of these orange vertices, I obtain an even cycle, and that's the only way how I get even cycles. Any cycle that picks up an odd number of these orange vertices will be even, and every other cycle will be odd. This is very important because this means that this graph here is a counterexample to the integral Erdős-Pozsár property of even directed cycles. This guy has lots of even cycles because there's lots of these orange vertices, there's lots of cycles going around, cannot delete a small set to remove all of them, but at the same time there's no two disjoint even directed cycles. It's kind of frightening for a multitude of reasons. One of them is that's a planar graph. So most of the time, if you look at these types of parity cycle packing problems, there is a topological aspect to it, and planar things usually are fine, or things embedded on surfaces that are orientable are usually fine, and this is way off of that somehow. So there's a lot that goes wrong, and half of this talk will be that I will just talk to you about all the things that go wrong, because this is just the beginning. So here's a timeline. So I start with kind of roughly in the middle here with the original Erdős-Pozsár result, where they just show that cycles themselves have the Erdős-Pozsár property. This is by Erdős and Pozsár in the 60s. And then for a while there was nothing, and then we got the grid theorem by Robertson-Seymour. This was a major turning point in graph minor structure theory, and this enabled a lot of results that kind of extended the Erdős-Pozsár property to different types of cycles. For example, in the end of the last millennial, Reed proved that odd cycles have the half-integral Erdős-Pozsár property, and then very recently, I think the paper was published last year, Thomas and Yo proved that cycles of any length unequal to 0 mod q have the half-integral Erdős-Pozsár property. There have been extensions to this theorem by people in this room, but I need space, so this is this is what I do. So here's the other side of the story, and here's what we know about directed graphs. So the Erdős-Pozsár property for directed cycles was conjectured, I think, in the 70s, if I remember correctly, 70s or 80s, and proven somewhere in the 90s by Reed, Robertson, Seymour, and Thomas. So it took a while, and this is a very complicated and deep theorem somehow, which manifests itself because this is the foundation of a theorem that came a couple of decades later, namely the proof of the directed grid theorem, now by Kawarabayashi and Kreutzer. And again, now having access to this fundamental tool in directed graph structure theory, this was by Kawarabayashi, Kreutzer, Kwon, and Shi. We could also kind of replicate Reed's results, so now we know that odd directed cycles have the half-integral Erdős-Pozsár property. So this is somehow what we know. There is a third aspect to the story, because I'm talking here about odd cycles and non-zero modulo q. What about even cycles? And there is a rich and deep history in some sense. So this is why the timeline is so long, because the deep history starts in 1913 with the question of Polya on the permanent of 0-1 matrices. So he asked he had some specific conditions, some specific technique, and he asked under which conditions on the matrices his technique would allow to compute the permanent. And then way later, people found out that in order to find an algorithmic answer to Polya's permanent problem, one would need an algorithm that decides whether a directed graph has an even cycle, which seems a weird problem to have. This indicates, like, at this point, no one knew, given a directed graph, how to decide whether there's an even cycle in the graph or not. And this continued. The algorithm, the first polynomial time algorithm for the even dicycle problem, was found in 1999. So almost 100 years after Polya's permanent problem, and surprisingly close to today's date if you think about this is just find an even cycle in a digraph. This should not be a complicated problem somehow. But this is very indicative of the types of problems we are having, because there's a lot to unpack. It's just to illustrate how complicated even-directed cycles can actually be. But there's a contrast somehow, because while even-directed cycles are very complicated objects to deal with, even undirected cycles are quite the opposite somehow. So here's a very short one-slide proof that even undirected cycles have the integral Erdős-Pozsar property. So this object here is a wall. It's this like hexagonal grid shape where I'm allowed to subdivide edges. And here's a version of the grid theorem that says that there's some function such that every graph with large enough tree width contains a large wall, so subdivision of such an object as a subgraph. I will not define tree width. It's also not really important what tree width is. Just think of it, there is some graph parameter that allows you to say if the parameter is big, you find a big object. And here's a slight alternative version of this by Thomason. He proved 2 years later that if you have a large wall, then in particular you can find a bipartite subwall in there. So you can get rid of all the odd cycles in the wall, which can occur because you can subdivide and you find something that's bipartite. You can find something even stronger where all of the degree 3 vertices in the wall belong to the same color class. So combining these two says if I have big tree widths, I find a big packing of even cycles. So the only case I have to analyze is the case where I have small tree width. And this will then result in what I said before, so even cycles indeed have the Erdős-Pozsar property. So here's a sketch. There's one leap I will make, and the rest I hope is kind of possible to follow. So I know I only have to consider graphs of small tree width. So I say G is a graph of tree width less than f of k, which is a minimal context sample. And I assume that there is a set, so suppose there is some set of size at most 3 times this f of k plus 1, such that if I delete s from the graph, there are at least 2 components that have an even cycle. If this happens, each of these components is not a minimal context sample anymore. So for each of these components, I either have a large packing or a small hitting set. And if in one of these components I find an L-1 packing, I have in total enough cycles to, I say L, this should be K minus L-1, sorry. I have enough even cycles altogether. Also L is at most K minus 1, because otherwise I already found my K cycles. But so if I have at least 2 such components, I'm happy. So this means I find in each of them a small hitting set, and because again the number of components is bounded, I delete a bounded number of vertices altogether with this set S here to remove all of the even cycles from the graph. And so this means for each such set that is small enough, there's exactly 1 component that has an even cycle. And this is the leap I'm taking. So if I have such a property for all sets of small size, this defines an object that's called a tangle. And the tangle witnesses that the tree width is large. And this is a this is a contradiction to my assumption in the beginning that I have a graph of small tree width. This is a very compact way to prove this Erdős-Pozsar property. This is not how we do it in the paper. This is just here for a presentation because it allows me to reduce the case analysis. You seem to.
Is it supposed to be a k minus 1 packing?
It's supposed to be k packing.
So in the first, if any of these components has a.
Yes.
Has
Yes.
A k minus, yeah.
Yeah.
Cool.
Yeah. There's
Yeah,
L and K very similar letters somehow. Sorry.
Okay.
So here's a problem. This would be all nice, but this theorem already fails in directed graphs. We've seen an example for this already. Like I took the grid that I get out of the directed grid theorem, I subdivide an edge of each row and have a grid without any even directed cycle. So I can't use this idea at all to prove anything about even directed cycles.
So you contains means just software, right? In here, the Thomason's
Yes, yes. So this is a nice little thing in undirected graph theory, sadly not usable at all for us. Here's another thing that's very nice. This is now about odd cycles. This is about so-called A paths. I will just quickly draw a picture. So an A path is you have some set of vertices A, and then an A path is a path that has both endpoints inside of A, and all other vertices are outside of A. So this guy here is an A path. And a lot of study has been done on these objects. These can also be packed. They have their own Erdős-Pózsa type results. These I'm going to use. So the thing is, the argument I made before for the even cycles, this can be generalized. In general, I can say that the situation I need to analyze is I have a big wall, and all of the cycles I want to pack are somehow in relation to this wall. Because otherwise I can make the arguments from before, reduce to small tree width, and obtain whatever I want by induction. So all I have to do is look at the big wall and look at my cycles that I want to pack or cover with respect to the wall. So here's the so-called A-path theorem. And this is very nice. So this says, if I take any vertex set A and any integer k, then I can either find k vertex disjoint odd A paths, odd means of odd length, or I find a very small set of vertices whose removal gets rid of all of the A paths. And this allows me to extend what we had before for even cycles now also to odd cycles. Because what I would like to have is that I have some sort of answer in the situation where the tree width is large. So assume I have a large bipartite wall W prime, this is this guy here, and let A just be the set of vertices that are the vertices of degree 3 in this wall. I just ignore the subdivision vertices and the corners of the wall. I also ignored it for some reason. I made the bottom row blue. Don't think about it. So this is my wall, and now I just apply the A-path theorem to the wall. And this has one of two outcomes. Either I find a small set that kills all of the odd A-paths, and because the wall was bipartite, no odd A-path exists, so suddenly I get rid of all of my odd cycles that are close to the wall. That's nice. So I found a cover. Or I find many of these disjoint odd A-paths that jump over the wall, do all sorts of things. But the thing is, I only want to find a bounded size packing. So I can assume there's a bunch of them. Their endpoints are somewhere in the wall, but I will still find a large area of the wall where nothing happens. I take this area and I analyze how these paths can be extended to attach to the outside of the wall. And then I find one of three outcomes after some normalization. I find this guy that has many disjoint cycles, or this guy has also many disjoint cycles, or the guy in the middle. This is now where all of these odd paths kind of pairwise cross, and this is exactly the situation where the 1/2 comes into play, because this guy does not contain two disjoint odd cycles, but has many that are half integral. So this is somehow a very rough summary of how to prove the odd cycle Erdős-Pózsa theorem. So this would be nice to use, no? This entire A-path idea would be great. So here's a problem. What we can do is we can take all of this, what we discussed before, and even this reduction to bounded or unbounded tree width, also in the directed setting. So this assumption in the beginning that the only situation you have to analyze is where we have a big wall, and then everything that is in even cycle is somehow highly connected to the wall, this assumption still holds. So we again are allowed to do some local analysis, essentially, of the structure for our graph. And we have the grid theorem, this is what I said before. Here I did not do the grid, this is now my wall. You can kind of see it, it's like a tower in some sort, but it still rotates. And it still has this nice property. All of the cycles have to separate the very inner face from the very outer face. So all of these cycles are kind of bound to behave in a certain way inside of this wall. And now what I would like to do is I would like to have an A-path theorem to say how do my paths attach to the wall to do something. Problem is, here's a theorem about complexity that says if you give me two vertices in a digraph, it's NP-complete to decide whether you can go from S to T with an even path. There's no way. And because this problem is NP-complete, it's very much unlikely that we find a nice structural description on how to deal with these things. Because, at least from experience, most of the time, if we find such a description, we find an algorithm. So unless something horribly goes wrong in complexity theory, we probably don't have a nice A-path theorem. Earlier I said people have proven the odd Erdős-Pósa theorem, and this is because here they can use a trick. So this is the lemma they use, and they talk about walks, not paths. So a walk is allowed to repeat vertices but not edges, and they say they can either find a half-integral packing of odd cycles, a half-integral packing of odd-directed A paths, or delete a small set that removes all of the A walks. And the reason for this is because if your walk is of odd length, one of two things happens. Either the walk kind of goes out, closes some cycle, comes back where the cycle itself is odd. That's a win, because we want to pack odd cycles. Or the path kind of leaves, could also again close some cycle, but maybe the cycle is even and return, but then this piece of the walk is an odd path. It's of course a simplified picture, but in general this is what happens, and this is why we have this nice thing. The trick of course fails if we talk about even things, because if I want to have an even walk, it can consist of an odd cycle and an odd walk, an odd path. So no use. You can essentially abandon the idea of using the A-path theorem. So what can we do? So far as everything has been somehow negative. Maybe it's time for some positive outcome. So here's a topological component to all of it. This is just a definition for a sort of minor relation on directed graphs. So I say that a digraph H is a butterfly minor of a digraph D if I can take some subgraph of D and then perform butterfly contractions to obtain H. And a butterfly contraction is just I'm allowed to contract certain types of edges. So I'm always allowed to contract an edge if it is the only incoming edge of its head, or if it's the only outgoing edge of its tail. These two situations are fine, these are safe, but if an edge is neither the only outgoing nor the only incoming edge, this is a situation I cannot reduce. And the reason is because, well, I could have a path that starts in the tail, ends in the head, and by contracting the edge, I could make this into a cycle where there was no cycle before. And this is a situation I want to avoid because I want to describe the structure of my directed cycles. So this is what a butterfly minor is, and here's the very first theorem that I am aware of that used butterfly minors. They didn't call it like this back when they proved the theorem. This is Simon and Thomason, and they proved, and it's a very strange theorem somehow, if you have a digraph, then this digraph has a subdivision such that the subdivision is completely free of even cycles. Then this digraph cannot contain one of these objects as a butterfly minor, where these are essentially take an odd length undirected cycle and replace every edge by an arc in each direction. And this is an if and only if, so the reverse is also true. If you don't contain these guys, then there is some subdivision that gets rid of all the even cycles. Because this is, for all digraphs, this means whenever you find a digraph, a subgraph that has one of these guys as butterfly minor, then you have a certificate that this subgraph contains an even cycle. So the existence of a certain type of minor immediately gives me even directed cycles, no matter what I do. Which is very nice because this has a lot of implications. In particular, and now it's very sad that Rutger isn't here, there's a structure theorem for these guys. This is the theorem that then allows us to detect even directed cycles. And this is a highly simplified version of the structure theory. So this says if you have a strongly two-connected digraph, then this guy falls into this family if and only if it's either the digraph that represents the Fano plane. So this is the this you get by taking the incidence graph of the Fano plane, taking a perfect matching, orienting all non-matching edges from one color class to the other, and contracting the matching edges. This is how this guy arises. Or you take strongly two-connected, strongly planar digraphs and glue them together under certain types of operations. I'm not defining them here, they're complicated, but it's essentially take strongly planar things, glue them together. Where strongly planar means you can draw them in the plane without crossings, such that no vertex has such a thing. So you cannot have a vertex where you have an outgoing, an incoming, an outgoing, and an incoming edge in cyclic order around like this. So for every vertex, the edges need to be drawn in essentially a butterfly, right? All the edges come in at one side and go out on the other. So these are very well behaved graphs. In particular, the grid or the wall we had before, they fulfill this property, while these odd cycles here, they cannot be drawn in such a way. What this means for us is that we now have a topological handle on some part of the problem. Because what we can say is that whenever we have an area that's supported by some substructure that's like a grid, and this area is free of even cycles, that this means in particular it must be free of these odd bicycles. And if they don't exist, then this area at least can be roughly described using the structure theorem. And this means we can assume that the areas we have got where we got rid of the even directed cycles are essentially strongly planar. I'm not going to explain what essentially means. This is a directed version of what in graph minus is called flatness. So it's not really planar, but it somewhat behaves like it. Let's, for the sake of the talk, just assume if I don't have an even directed cycle, I'm a planar graph. This is more or less what happens. Okay. So the very first step I would need to do is I would need to prove that if I have a big wall, I find an area where there's no even cycle. And this area should be nice somehow. So here's two guys. This is two ways you could have something very non-planar happen on your grid structure. And in each of these cases, you can find three directed cycles that are interconnected in a nice way. So in both of them I kind of marked the cycles, both of them reduced to this object, if you redraw the cycles. And you can see that this object now contains a bidirected triangle as a butterfly minor. So this up to subdivision is a subgraph of both of these guys. And this edge in particular is butterfly contractible because it's the only outgoing edge of the tail and the only incoming edge of the head. So I can contract, identify these vertices, get a bidirected triangle. So both of these guys, no matter how they're subdivided, must contain an even directed cycle. Can never get rid of them. So this I can use because this means there's a very small jumping structure I need to certify the existence of even directed cycles. And this means if I take a big cylindrical wall, if I have many disjoint parts that kind of jump far in the wall, I immediately get many of these guys, so get many even dicycles, I'm happy. So this means there's a small set I can remove to get rid of all of these jumps. Assume there's no jumps. So what I can do now is I can kind of partition the many layered cycles in this guy into many layers. Each of these layers, let's say this guy, consists of some buffer zones. And these buffer zones need to be just big enough such that I can make sure that if there's something that starts in here and jumps outside, it must end inside of the buffer zone because otherwise it would certify one of these long jumps. So I can have many of these guys that are kind of protected by their own buffers. And if I have k of such layers, I can ask each individual layer, do you have an even cycle? If everyone answers yes, I found k even cycles. So one of them says no. And this means I find a layer that's completely odd on its own. This will be my starting point. So I can immediately compress the entire structure down to an annulus grid there's two faces, and these are disconnected. They cannot really jump over, because jumps over would again make many of these guys happen. These two faces can contain even cycles, but the ring separating them is completely odd. So this is my starting point. So let's recap a little bit. I think this is a good point. So it would be nice if we could find some sort of substitute for the A-path theorem, but probably no hope for this. But we have a little bit of handle. We have some tools at hand. So we have some topological argument regarding these odd bicycles that generates even dicycles. It's a bit of a conundrum here. So odd bicycles always have even dicycles. We can somehow guarantee that if we have an odd domain, so an area in the graph where there is no even cycle, then this behaves in a nice topological way, so strongly planar. And if I have a large grid-like infrastructure, I either find a half-integral packing, in this case even half-integral of even dicycles, or I can find a big odd domain inside of this grid infrastructure. This is 3 tools we have seen so far. And these tools in some sense replicate the main tools that were used to prove the so-called graph minus structure theorem by Robson and Seymour. So this will be our strategy. So the remainder of the talk will talk about how can we use these tools to replicate a miniature version of the graph minus structure theorem in the directed setting to then prove the Erdős-Pozsár property. And to do this, the key thing we have to discuss is there a way to expand our odd domain? So we in the previous slide we've seen if I'm given a single cylindrical grid, I can find a big odd cylinder inside, but there's still these 2 even faces. And now what I would like is I would like to kind of carve out pieces from these even faces and make them odd and push them into the odd domain, make the odd domain grow until the places where even cycles happen are few and are somehow more controllable, less chaotic. And the way we're going to do this is we start out with our cylinder, and then we ask for large linkages that start on one side of the cylinder, run through the even area, and then connect into the cylinder again on the other side. And if we kind of manage to maintain lots of directed cycles around the even domain, then this allows us to proceed with this kind of carving in a recursive way. So if we start out with this cylinder, we find this large linkage, make it kind of nicely behaved, split the even domain into pieces, and then each piece itself will be protected by its own small cylinder that is odd. We can repeat this over and over until we run out of paths. This will be the general strategy. Before we start this, there's something to discuss here. And this is kind of the first lemma we found when thinking about it. Because the problem is, of course, I can expand this odd domain, but still even cycles could run through the domain. I could have an even cycle that starts on one of the 2 even faces, goes through the odd domain, and then contains something on the other side. And maybe all of my cycles are like this. Maybe all of my even cycles connect several of the even faces at once. So the lemma here says, if you give me 2 directed cycles, one of them even and the other one odd, such that their union is a planar graph, then it's relatively easy to see that there must be some even phase somewhere. But in particular, there must be an even phase that is a directed cycle. And this phase must sit in one of the 2 disks that is defined by the odd cycle. Of course, this is an oversimplification because all the time I say essentially planar. So we need to do a lot of work to extend this to our essentially planar embeddings, but it works. So we can say whenever we have an odd cycle and an even cycle that are somehow interconnected and touch our odd domain, then there must be an even cycle that sits on one of the 2 sides defined by the odd cycle. And this is kind of nice, because now look at our cylinder here. The cylinder has 2 boundary cycles, this one to the outer face, this one to the inner face. And now if there is some odd cycle that completely chaotically goes through everything, this argument says that there also must be an even cycle that's either completely in here or completely outside. So it somehow certifies that the only cycles we need to control are those that are confined to a single even area. That also means if at some point we find k disjoint even areas, we win, because then we have k even cycles. Which is important because in some sense we need to be able to bound the number of even areas we generate. Okay. So this is now the tools we have, and now we can start to try to expand the odd domain. And the first thing is, so what we want to do is we want to integrate many of these paths that shoot through the even phase. And we kind of know that every area locally hosts an even cycle. So this what this says here, whenever I find so many cycles, I can integrate them in a cylinder, as you've seen in the previous picture. And this means I can reapply the odd wall argument from the beginning. So whenever I find this large linkage, I can make it odd. But there's two questions. So the first one is, this thing here needs the path to be parallel. They need to be somehow planar in the beginning. So what if they're completely chaotic? And the second question is, even if they're not completely chaotic, what happens if lots of stuff jumps over them? So here's my picture with lots of chaotic jumps that just go somewhere. And I'm using the idea with the odd bicycles again. So this guy here contains an odd bicycle by one of the previous pictures. And because this grid infrastructure here is big, and I have many of these jumps, I can fit a whole bunch of those guys into my grid. So if I find many chaotic jumps, each of them, where I can sort these paths into pairs of that form crosses, I can find many odd bicycles, and many odd bicycles means I have many even dicycles. So I can assume there's not a lot of these chaotic jumps. And this also means, suppose I find this kind of strip I can carve out, then of course from this side to this side I cannot jump over the strip. Because if many paths jump over, then that's just a more orderly version of this picture. So many jumps jumping over again means I can pack these sort of crossing things with the little cycles around. So this is kind of nice. This allows me to really split the area every time I find such a large collection of paths. So now we have to examine how to fully propel the induction forward. And maybe some of you have already seen this. There is kind of an issue. So I said I want to maintain that my even area is surrounded by a nice collection of concentric cycles. So here is my even area from before. I find this large family of paths that goes through, and now each of these even areas needs to be protected by a family of cycles surrounding it, which is nice for the left side. But what is going on to the right? So to the right, what I have is I have these paths going here, and I have these paths going here, and they just don't form a cycle. But what I have is I have kind of this additional infrastructure from the other side. So what I'm going to do is I will keep both of them, and both of these families can be completed to a cycle family by using the stuff from the hinterland. This is a little bit artificial, and this is the source of almost all of the following difficulties. Like this is analyzing this substructure is the complicated part, because here there is some sort of symmetry. Any sort of family that jumps, anything that happens is kind of nice. But this now has a direction. This is now inherently directed, and that will come up on the next slide with more issues. Just for some terminology, so if the even area is surrounded by just cycles, this is a circle area. And if the even area is surrounded by two parallel path families that are connected to a cycle somewhere far away, this is a diamond area. I don't really go into this in detail during the talk, but these objects here are the main reason why at the moment we only have quarter integral, because when analyzing this and understanding how the cycles like the even cycles behave with respect to this infrastructure, this is where we have to make some sacrifices. But there is not really a way to avoid this. Kind of in analogy to the word vertex, which was used for these areas in graph minus, we call these maelstroms because they're more chaotic, more wild, lots of more stuff can happen. And we have circle maelstroms and diamond maelstroms. Okay. So we're out in the ocean. We want to chart the area. We can kind of find the nice streams where we can safely sail and understand where are the tides that we have to avoid, like the little things in the sea that make travel hard. And most of the arguments were perfectly nice for circles, but there is some danger hidden inside of the diamonds. So here's my diamond. I've redrawn it a little bit differently. So here's one of the two parallel families, here's the other, and then here in the hinterland are the paths that make my cycle happen. And so now here, what I'm going to do is I try to split this now, right? I need to expand my domain into this diamond by finding new path families to cut through here. And then I need to be able to split this even area inside here into two new pieces. This can happen in many ways. Here's one way, so I could go from blue to blue in the direction of blue, and that's kind of nice. It's a little bit small, but you can see I can essentially make a diamond here, and then make a new diamond here. So I got one diamond, find a path family, make two diamonds out of it. And there's enough cycles in the hinterland to connect. Same happens.
So how do you connect this for this left diamond here?
This one?
Okay, that's right.
Ah, it's here. So the cycle family now goes in here. So the hinterland cycle family will come up to here and leave from here and then connect through the cycles.
Yeah.
And then it's only these two parallel paths.
Works for this, yeah.
Picture is very similar if I go from yellow to blue. If I go from yellow to blue, it really doesn't matter. And similarly, this is another way I could go from yellow to blue. I could also go like this. But again, you can see, so here is one diamond, and here is another diamond. And again, many cycles in the hinterland to connect them. But there's a fourth way. So what happens in this situation? There is a cycle here. But if you look at this structure a bit more carefully, so the connectivity structure now is I have this path going here, then I have a path that kind of enters here, and then this goes against, and then it leaves here. So I have these two vertices that are oriented opposite directions. So this is neither a circle nor a diamond. So what should I do? So the kind of nice observation is that locally this again forms a circle area. So this situation here is a circle, or what we call it an eddy, because it's a smaller swirl inside of the big maelstrom, draws us deeper under the sea. And this is really where it becomes difficult, because this can propagate as much as you want. So you have this guy, so you have a guy that goes backwards, then on this guy going backwards, you can again have guys going backwards. Interestingly, locally, this always looks like a smaller version of the bigger structure we've built so far, because locally this is some cylindrical grid with two areas around it. But this can go on forever. So this defines somehow this recursive structure that is hidden inside of the diamonds. Still, luckily, the amount of even areas we can find in the end is bounded by k. And eventually, we run out of these path families. So eventually, deep inside of this recursion, there's no way to connect these growing branches to anything else in the diamond. So all of these can be cut off and can be handled separately. But this takes some effort.
So you have to cut off the tentacles of the beast.
Yes. It's very necessary. It's also a very good segue into the last slide. Because I will not talk about how to handle this in detail because it's horrific. The definition to define this recursive structure is more than 2 pages long. What I will talk about is the nice and simple case where we have a circle and we run out of paths. So we have a circle, but there's not enough paths to continue building the odd domain. And now we want to deal with this circle to fully remove all of the even cycles that intersect the graph here. I just reiterate here, if at some point I find k distinct even areas, I have my packing. So most of the time when I try to extend the odd domain, one of the 2 sides will be odd. Here we are very lucky because it's the diamond side that's odd. And here again, it's very good. It's a nice case. So it's only the circle side that remains even. And maybe now we don't have large families of paths anymore. Maybe now any family of paths that starts somewhere here runs into a small separation and is blocked from re-entering the grid. What we can do now is we can identify this boundary here and we can select segments. So we know whenever we find a segment, on this segment there cannot be many paths that start here and go somewhere, but also there cannot be many paths that start somewhere else and enter the segment, because any of these things would allow us to expand the odd domain. So there's a small separation here that separates this part from the rest in both directions. So it can neither enter nor leave. And we can select this segment minimally with the property that after deleting the separator there's an even cycle inside. Or at least there's an even cycle that connects here and then it kind of leaves somewhere else, but with the shifting arguments from before we can prove that there is one that lives completely inside. And then we continue. We kind of really build these segments one after the other, each of them certifying the existence of another even cycle, until we just completely run out of space here. If this procedure gives us k segments, then we find our packing, because each segment certifies the existence of one cycle. So if we find many that are kind of on the surface, this is a good case. And this means the number of segments we find is bounded by k. And for each of these segments, by minimality, if we would go in a little bit more on the inside, we found a second separation that separates the inside also from the outside. But the separation for the slightly more inside guy, by choice of these segments, suddenly removes all of the even cycles that touch it. Because this was minimally chosen such that there's some even cycle. After removing the separators, if they go inside, remove the separator, no even cycle exists. And because I only found a bounded number of these guys, I can remove all of the even cycles that touch here altogether. And this resolves the last issue, because these were the big leakages where the even cycles could escape. After patching up every even area like this, what remains is still a big portion of our wall. And now the entire strong component that attaches to the wall, after deleting a sizable but bounded size set of vertices, is free of even cycles. And that's what we wanted. Right? Because this is the case where the rectangle points to the wall, but the wall does not see any even cycles. So this is how it's done, and also at the end of the talk.
Thank you. Surprised that you prepared in less than a week. Right. Any questions?
I have a curious
Yes.
thing for the beginning. So you make an example where that there are no two even directed cycles.
Yes.
So, which means that every directed cycle is old, right? Can you given any L and M, you can modify the word so that every cycle is the length L modulo M?
We didn't try. I would not be surprised if this is possible. What I can tell you about this is, so I have this theorem on these odd bicycles. There is a similar theorem that generalizes this to cycles 0 mod q. So there's for each q there is a sort of families of instructions that cannot be subdivided to remove the 0 mod q cycles. So I guess if these two combine, there could be a generalized version of this entire thing, if one wants to go through the thing. Yes.
So when does the border packing come in?
I didn't fully explain this. I go back here. So one of the sources for this is, let's go back to the picture without this. Here. So one of the situations that can occur is that here you find crossings, and these crossings can go backwards or from one side to the other. And this can happen in a way that, because like to make this crossing into an even dicycle or an odd bicycle in the first place, it needs to be kind of routed back to the cycle family. But if this goes backwards, it intercepts itself when you try to route back. So we have ways of dealing with this.
Yeah.
This is like the way we deal with this is by using matching structure theory. So we expand into a whole different area somehow. But after we come back, we still need to make an argument that this is somehow routable, and this routing needs more space.
I see.
We think there's an easier way to do it, but we were happy to have
So
something.
you sort of have two steps. You get some sort of half integral packing perhaps, and then you translate that, but at each step you lose a factor.
Locally somehow. So when you have this guy and you find a large linkage that connects, inside of this large linkage we find a half integral packing of some object, and this object then needs to be immersed into the actual digraph, and then you it kind of bites itself sometimes, and then you have to do some local surgery.
But in the end, now you believe the half thing anyway. But
I think that it should be everything should be half.
everything should be half.
Yes, I think it works. Modulo details. I'm still afraid of the abyss.
Yeah.
Does this give an algorithm as well?
Yes. So in the end, so everything is FPT. So what we can compute is, so in the end what we would get is a directed 3D composition, whatever this is exactly. But think of it as a tree-like thing where the vertices live in blobs along the tree. And whenever you have a cycle that comes from the vertices here and then connects to the vertices here, it needs to go through some set that lives on the edges. So there's a small set of vertices that blocks anything that goes here and comes back. And the additional property we have is that each of these bags contains a small set whose removal deletes all even cycles that interact with the vertices here and that go through here. And this decomposition we can approximate with bounded size of these sets in FPT time. And then this would allow us to do some dynamic programming to actually either find the cycles or remove them. And this can also be applied to solve things like the disjoint path problem. And you can even count matchings for some reason.
Any other questions?
Do you have any idea what obstacles to an integral Erdos-Boser look like?
So I showed you this one in the beginning. Let me make another drawing. That's a very good question. So one of these obstacles was this guy where so like this, where you had these objects like that on the outside, and then you subdivide it here such that all of these cycles are odd,
Yep.
and then you jump. Another version of this would be, so you still orient like this, but now what you could do is you could do local crossings on the outside. These are completely incomparable. You can make this such that the only way to like fully understand how the even cycles behave is by finding the odd bicycles that are guaranteed to exist because of these crossings. And at some point we had at least a third guess that seemed to be incomparable to those, but I forgot what this was. So.
Yeah.
It's overall very messy.
Sure. But how? So, I guess you already know several different families.
Yes.
But yeah, maybe difficult to know when you get to the end of the list.
I think the way to find them would be, because this is somehow what I described here in the end. What you find here is you have this large cylinder surrounding the area, and then you have these cycles that go from the cylinder into these areas.
Yep.
So this is essentially this situation.
How can they look?
So all of these guys must live on the boundary of these maelströms.
Okay.
So if you go in and analyze this, then at least for the circles you should get something. I am afraid of the abyss. So
The abyss looks terrifying.
yes.
Does this imply that the list of obstruction families is finite? Or is that even not clear?
To be honest, I think it's not.
It's not.
Oh, interesting.
Or at least it's highly non-trivial to make it finite. This is because butterfly minors themselves are not a well quasi-order to begin with. So there could be weird anti-chains to how these objects relate to another.
Right.
And that's kind of...
Right. Any more questions? If not, let's thank the speaker. Okay.